All right, well, let's go ahead and do an example where we are energizing a coil. Actually, let me grab my calculator first so that I don't have to do it later. All right, so what we're going to do is we're going to draw a source. Let's say it starts at 0 and pulses up. Also, I want to just note real quick that I've been drawing some circuits where I've got a voltage source and a switch. I've been drawing some where I just have a pulse source. I want to, if I haven't clarified that already, I just want to make it clear that they're all equivalent. And if you don't see why they're equivalent, feel free to ask. But I see them as equivalent, so I change between them a couple times. This is what we're going to see in LT Spice most of the time, so that's why I use the pulse source in a lot of the example problems. But when I'm deriving stuff, it's just as easy to just draw a voltage source with a switch or some other equivalent like I did in the previous video with the current source, just to make everything work out. But it's important to recognize those as equivalent. Okay, so let's say I have an RL circuit, and let's say that I have a 1 millihenry inductor and a 10 kilo ohm resistor. Okay, and let's say that my source pulses from 0 to 10 volts at time t equals 0, right? And so what I'm interested in this circuit is IL of t. And let's say that we're interested in determining what the current is, IL of t, as a function of time, okay? And let's just not bother about finding the current at a particular time. I can't eyeball this and figure out what the time constant is, but let's just go ahead and solve for it. We know that tau is equal to L over R for a RL circuit, and so in this case it's going to be 1 millihenry divided by 10 kilo ohms. So let me throw that in my calculator and see what that gives me. That gives me 100 nanoseconds, okay? All right, so if I wanted to plot this as a function of time, I would plot 1, 2, 3, 4, 5, 6 tau maybe. So this would be 600 nanoseconds, this would be 100 nanoseconds, and so on. And that would be t. And I'm interested in plotting IL of t. Well, what's the initial condition? I haven't given yet, but let's just say that I gave you the initial condition. IL of t equals 0 is equal to 0, right? So there's no current flowing in the inductor when this voltage source is at 0. Of course, that makes sense because at DC, my inductor is a short, so I would have 0 volts here and I'd have 0 volts here. And so I would obviously have no current flowing through my resistor, which means I would have no current flowing through my inductor. But what happens when I pulse this source from 0 to 10, so now sometime later, my voltage goes up to 10 volts, right? It goes pulsing up. And what happens is that my inductor current cannot change instantaneously. And so this node is also going to jump from 0 to 10 volts as well. And then this voltage will bleed off exponentially as this current rises exponentially, okay? And so let's go ahead and go back a slide and just pull our energizing the coil equation in. We can go ahead and use this equation to write it out. So it's going to be IL of t is equal to IL final. Well, let's figure out what IL final is. If you remember correctly, I said that, this is going to bleed off to 0. And so in the final case, I'm going to have 0 volts here and 10 volts on the other side. So I'm going to have 10 volts minus 0 divided by 10K, or 1 milliamp, right? And so that's my IL final. And so I can write that IL of t is going to be equal to 1 milliamp multiplied by 1 minus e to the minus t over 100 nanoseconds. Sorry, 100 nanoseconds. All right, that's my expression for IL of t. And then if I wanted to just roughly sketch this, I would have my current peaking at 1 milliamp at around 500 nanoseconds. That's right where it would reach. So I would have something that looks kind of like this. Right? And that would be my behavior for IL of T in this energizing the coil case, right? So if I was like saying, oh, I'm interested in finding the current at 100 nanoseconds or at 200 nanoseconds, I could obviously take this value for T, plug it into this equation. Oh, sorry, not plug it in there, but plug it in here. And then whatever this equation spits out, that would be the value of my current at that time T, okay? So that'll pretty much do it for this example. And then the next video, I'll go ahead and solve another quick energizing a coil example.